In part 3 of Module 6, we're going to continue our discussion of entropy change, and we're going to start this part with 2 example problems looking at what we studied and what we derived in part 2. So the first example problem says a 30 kilogram aluminum block initially at 140 degrees Celsius is brought into contact with a 40 kilogram block of iron at 60 degrees in an insulated enclosure. So we can sort of start this problem by looking at drawing a little bit of a diagram to define what it would look like. So we know that the system is insulated, so we're going to add some insulation on the outside. And we know that we have aluminum and iron coming into contact. And from this contact, we're told to determine the final equilibrium temperature, which we know how to do, and the total entropy change for this process, which is a new part. Okay, and we're given that we have a 30 kilogram aluminum block, so we have 30 kilograms of aluminum, and we're told that it's initially at 140 degrees Celsius. And for iron, we have a 40 kilogram block with a temperature of 60 degrees Celsius. And they come into contact, and we're supposed to find the final equilibrium temperature. So to find T equilibrium, we know what to do. We use our first law, which is Q in minus work out is equal to delta U plus delta KE plus delta PE. And this is a first law analysis. And we can cancel out a lot of things. If we look at the system as a whole, so let's look at the system as a whole, not just the aluminum or the iron. So our control volume or control mass is delimited by the green line. It means that Q in is going to be equal to 0. Work is going to be equal to 0 as well. We have nothing moving in our system. And we don't have any information on kinetic and potential energy, so they're also going to go to 0. And so we finally have that our equation simplifies to delta U is equal to 0, just like in our midterm exams. Now, we can separate this delta U for the aluminum and the iron. So we can say that delta U of A, which is aluminum, plus delta U of iron, which I'll just put delta U of I, is equal to 0. And going further than that, we also know that it's equal to MC T2 minus T1, all for aluminum, plus MC T2 minus T1, all for the iron. And we know that T2 is equal to T equilibrium. So we know that the T2 in the two cases is equal to T of our equilibrium. Now, our C for aluminum is, we know that T1 is equal to 140 degrees. Okay, so from this, we're going to have to find a C average in our tables. So we know that the aluminum can go from 140 degrees all the way down to 60 degrees. Okay, we have aluminum and iron, so we know that the final temperature is going to be somewhere close to between 60 and 140. So maybe like 100 or something like that. Okay, and so we're going to have to look for a C average at that temperature. So we are going to assume, or we're going to guess, that T2 is going to equal to 100 degrees Celsius, and therefore the average temperature is going to be T average guessed, okay, is going to be 120. Okay, I'll put like squiggly equals just so we know that it's an approximation. So 120 degrees plus 273 is equal to 393 Kelvin. So we're going to guess our C average at the closest temperature. So C average is going to be at 400 Kelvin. So if we go to our tables and we go to our aluminum, in table A3, so in table A3, we have solids and liquids, and we see that here we have some values for aluminum. And we see that they're all in Kelvin. So we're going to use the value at 400 Kelvin. We're going to assume that our T average is going to be close to 400 Kelvin. Now, this might be wrong and we might have to redo the problem, but we assume that we're going to be pretty much close to that in terms of our temperature. So our average temperature we think is going to be around 120, which is 393. So that's pretty close. And we can actually redo the problem after once again to check, but usually that's going to be somewhat of what we would have. And again, this can be different, but we'll see. So our T average at 400 Kelvin is equal to 0.949 kilojoules per kilogram Kelvin. For iron, it's a little bit easier. We have T1 is equal to 60 degrees, but for iron, we only have one value in our table. So our C average, we just use the value in our table that we have for any temperature. We're not given any other temperatures. So we just have 0.45 kilojoules per kilogram Kelvin. Okay, so if you go to your tables, you would get the same value. And now we have all the information that we need to plug into our values. So we plug in our C, our M for both items. We have our T1 for both items. And we find that T2 is equal to 382 Kelvin, which is equal to 109 Celsius. So I'm not going to go through all the steps because we already know these steps from previous modules. However, that's how you would find it essentially. You would just rearrange it to find T2 as a function of everything else. And we see that T2 is equal to 109 degrees. So now we have our guess has to be checked. So we need to check this guess. And we see that this guess was actually pretty good. So we have 109, so our T average would be a little bit higher. So 109 plus 140 would yield an average temperature of 124.5 degrees Celsius. So T average was actually 124.5 degrees Celsius, which in Kelvin is equal to 397.5. So we were okay with guessing 400 Kelvin. So we can say that C average at 400 Kelvin worked. We were actually very close to that value. Now, to the new part of the problem. How do we find the total entropy change? So the second part of the problem asks us to find the total entropy change. And in order to find the entropy change, we're going to be using our equation for solids and liquids. So we're going to use our solids / liquids equation, which we derived in part 2, which says that S2 minus S1, okay, and these are capital S, is equal to MC times ln of T2 over T1. And we're trying to find the total entropy change for the whole system. So this is for the system. But the equation can only apply to each item. So we need to apply this equation per item. So we need to apply it to aluminum and we need to apply it to iron. There's not one equation that brings it all. So what we're going to do is we're going to try and find the delta S of aluminum and the delta S of iron. So our delta S of aluminum is going to be equal to the following. It's going to be equal to 30, okay, which is our mass of the aluminum, times 0.949, our C for the aluminum, multiplied by ln of 382 Kelvin over 413 Kelvin. Remember that it's very important to put our temperatures in Kelvin, okay, for this. And we get a value of delta S for aluminum, I'll put a small a for aluminum, is equal to minus 2.221 kilojoules per Kelvin. Okay, we do the same thing and we repeat the same thing for delta S of iron, and we get 40 times 0.45 times the natural log of 382 over 333, and we get a positive value, 2.472 kilojoules per kilogram. And so we see that one is positive, one is negative. The reason one is positive and one is negative is that we have one that's increasing in temperature and one that's decreasing in temperature. So we have a spread of energy going from aluminum to iron, essentially. Okay, the aluminum starts at a higher temperature and spreads its energy to iron. Okay, so the delta S total of the system is now equal to essentially the sum of both. So we have delta S of I plus delta S of A. And just make sure you keep your signs correct. And if you keep your signs correct, you'll see that you get a positive change in entropy, which makes sense. We always usually have an increase in entropy within a system, or we have zero change in entropy. Okay, we either have an isentropic system or we create some entropy when we have heat transfer, essentially. Okay, so we never can destroy entropy. We never can go backwards in entropy overall in a system. Now, the S that we calculated was capital S, okay? What you can also do is you can find specific S and then multiply by mass. So just to remind you, capital S is equal to M times S, which is our specific value. Okay, so just making sure that that's clear for everyone. And the S specific would be equal to, so S specific, the lowercase s, would be equal to C ln of T2 over T1, just not multiplied by the mass. Okay, so the next problem we're going to do, so that concludes our first problem. The next problem we're going to do is a problem using ideal gases. So let me copy it over from our handout. And we have a question that says a piston cylinder device contains 0.75 kilograms of nitrogen gas. So we know that we have nitrogen gas, which is N2, at 140 kilopascals and 37 degrees. The gas is now compressed slowly in a polytropic process during which PV to the 1.3 is equal to a constant. And we're told that the process ends when the volume is reduced by half. Determine the entropy change of nitrogen. Okay, so for this problem, what we're going to do is we're going to first draw a little diagram of what we have. We have a piston cylinder device, and we're told we have a polytropic process, and we have state 1 and state 2 for our system that are defined, and we know that PV to the 1.3 is equal to a constant. Okay, that's for our polytropic process. And we know that at state 1, we have pressure 1 is equal to 140 kilopascals. We have temperature 1 is equal to 37 degrees Celsius. And we have a mass of 0.75 kilograms. At state 2, we're also told that V2 is equal to V1 over 2. Okay, so essentially V1 is double of V2. Okay, and we're told to find the change in entropy. So the change in entropy is capital S. Okay, and we know that the change in entropy is equal to mass times a change in lowercase s. Okay, and this is equal to the mass times one of the two equations that we have for our ideal gases. So we can use one of two equations. The first equation we could use is CV average times ln T2 over T1 plus R ln V2 over V1, or we could use the following equation. We could use CP average times ln of T2 over T1 minus R ln P2 over P1. So we can elect to choose whichever we want. Now we're going to use, in our case, we're going to use our first equation. We're going to use this one. We're not going to use the second one. The reason we're not going to use the second one is because in the first one, we already have a relation for volume between state 2 and state 1. In the second equation, we would have to find P2, which we can find, but it's an extra step. So we would have to find P2 for the second one. So it's an extra step. And therefore, we just try and keep it simple and we say, let's use the simplest equation, the one that has the most information on it. Now, you could have very well chosen the other one. It's completely fine, but you would have to find pressure 2 in addition to what we already have. Okay, so let's do a summary of what we already have. So we have V2 over V1 because we know that V2 over V1 is equal to 0.5. Okay, if we divide V2 by V1, we see that we have a half. We can find R for nitrogen. R for nitrogen is equal to 0.2968 from table A1. Okay, I'll let you go look if you want to go look and double check. And we already have temperature 1. We're trying to find temperature 2. We don't have temperature 2 yet. And we don't have CV average. We do have mass, however. Mass is 0.75. We're given that mass, and that mass does not change. So from this, we can now try and find our temperature 2. So we have to find temperature 2 and CV average. So it's important to do this in order. We want to find T2 first because to find CV average, we need the average temperature. So we need to verify what the first temperature is and what the last temperature is, take an average so that we can find the average CV. So how do we find T2 for a polytropic process? Well, T2 for a polytropic process, we need to apply our polytropic equations and sort of solve our problem using that. So if you remember, we have P1V1 to the 1.3 is equal to P2V2 to the 1.3. And using this relation and the fact that we have an ideal gas, we can substitute in values for pressure to find a relation between temperature and volume. Now, we had already summarized these relations for polytropic processes back in an earlier module. So I'm not going to go through the derivation once again, but you'll see that you have T2 over T1 is equal, so just by rearranging these equations, you have T2 over T1 is equal to V1 over V2 to the power of the n minus 1. Okay, and you can use uppercase V or lowercase v, it doesn't matter. It would be the same thing. Okay, and you would have that this is equal to 2. Okay, and we know the value of that. So we know temperature 1 and we know n is 1.3. Therefore, we can solve for T2. So T2 is equal to 310 multiplied by 2 to the 1.3 minus 1. And this is equal to 381.7 Kelvin. Now, from these relations here, from the two relations that we have here, we could also find pressure if we wanted to. We could find pressure 2. Remember, for our polytropic process, our pressure 2 over pressure 1 is equal to V1 over V2 to the power of K. So we could find pressure 2. But that would be an extra step that we don't need to do this time. We just need to find temperature 2 and then we can solve our problem. And we have to find our CV average. So this is not going to be used. We're not going to use this, but we could use it if you were using the other equation. But now moving forward, we have temperature 1 and temperature 2, so we can find our CV average. And in order to do the CV average, we have to find our average temperature. So we have a temperature of 310 plus 381.7 divided by 2 is equal to 346. Okay, so our average, T average, is equal to 346 approximately. So we're going to have to round that 346 Kelvin, sorry. And we're going to round that to the closest value that we have in our tables. So now if we go to our tables, and we can go to table A2 for gases, and we have a bunch of different gases, and we can see that our average temperature should be around 350. So let's look for a value at 350. We have nitrogen there, a value at 350, and we're looking for CV at 350. So we're going to be looking for this value right here, okay, which was already highlighted from a previous problem, but just to redo it, you can see that that would be the value. So we have that CV is equal to 0.744. So CV average is equal to 0.744 because that's the closest value to 346 Kelvin. It's at 350. So now that we have CV average, we can just compute our delta S by plugging in all our values, and we get that our delta S is minus 0.0385 kilojoules per Kelvin. Okay, and that concludes our problem. We found our change in entropy within this polytropic process. Okay. Now, the next thing we want to talk about is, after having done these example problems, is entropy change for a control mass for an irreversible system. And we're going to derive a little bit of what happens if we have a control mass for an irreversible system and not a reversible system like before. So let me write the title. And here, what we're going to do is we're going to take the same example as before with our reversible processes, and we're just going to add a new process to describe what is happening. So we're now looking at irreversible system. Okay, so let's say we have a PV diagram and we have, as usual, a process A that goes from 1 to 2 that is reversible. Okay, we're going to have a reversible A and then a process B that is reversible as well. And now we're going to add to this an irreversible process C. So C is now going to be irreversible. Okay, so not like before where we had it reversible. C is going to be irreversible. Okay, so we know that if we go through process A plus B, we have a reversible cycle. So A plus B is a reversible cycle. And if we do the closed integral of dq over t, we say that this is equal to the integral from 1 to 2 of dq over t plus the integral from 2 to 1 of dq over t for A and B respectively. And we know that this is equal to 0. By definition, if we have a reversible cycle, we know that this is equal to 0. We know that the closed integral of dq over t is equal to 0. Now, if we look at our process C plus B, so if we look at C plus B, we now have an irreversible system. And an irreversible cycle, essentially. Okay, and if we do the integral, the closed integral of dq over t, we would have the process from 1 to 2 of dq over t for process C plus the integral from 2 to 1 of dq over t for process B is now less than 0. So remember, when we have an irreversible cycle, the closed integral of dq over t is less than 0. It has to be less. Okay, the best case scenario is that it's equal to 0 and we have a reversible cycle. And what that means is that if it's less than 0 and B is the same process, so B is a reversible process, what that means is that we can say from this that the integral from 1 to 2 of dq over t for A has to be greater than the integral from 1 to 2 of dq over t for C. It has to be a greater value because one is equal to 0 and the other one is equal to less than 0. So we can write that, so we have that definition. And now what we can say is that we remember that entropy is independent of path. Okay, we had derived earlier that entropy was independent of path. The change in entropy didn't matter as to the path. So what does that mean? Well, that means that we can write also that the integral from 1 to 2 of dq over t for A is equal to the integral from 1 to 2 of ds, okay, I'm just changing the sign so it's a little bit easier to write, is equal to the integral from 1 to 2 of ds of A, which is also equal to the integral from 1 to 2 of dsc. Okay, so now we can say that this term here is equal to each other because path A is a reversible process, but we can also say that this is equal to each other because entropy is a property. It depends only on the initial and final states. So if the initial and final states are the same, we can say that the change of entropy in A and the change of entropy in C should be the same. Now, what does that mean? Well, that means that, therefore, if we look at our two equations here, this first one and the second one, there's something weird here. There's something that's not working out. And what's not working out is essentially, we can say that, therefore, our actual integral from 1 to 2 of the change in entropy for an irreversible process is going to be greater than its reversible definition, than dq over t for process C. It has to be greater. Okay, so we just said that just to recap, so let's go back to the top equation, okay? So this one right here. So we said that the integral of dq over ta has to be greater than the integral of dq over tc. And we also said that if the integral of dq over ta is equal to the change in entropy of A, it means that it's also equal to the change in entropy of C. So that means that the change in entropy of C, going back to the bottom equation, has to be greater than the change in heat over temperature. So the definition of S2 minus S1, or the change in entropy for an irreversible process, is not equal to dq over T. It's equal to something else. And that makes sense, okay? It's equal, there's something added to it that we have to add. So what we can write is the result of this is that, and this is true for, let's just add here that this is true for irreversible systems, okay? So if we know this irreversible process, so if we know this, we can generalize and say that ds is greater than dq over t. And this is true, greater than or equal to dq over t. And we agree with the statement, this is true for reversible and irreversible. It's true for reversible because it's equal, and irreversible would be greater. So we know that S2 minus S1 is greater than or equal to the integral from 1 to 2 of dq over t. Okay, and that's going to be a very important relation to follow. And we know, once again, we know that ds is equal to dq over t for reversible, and ds is greater than dq over t for irreversible. So what we've been able to do with this little derivation here is to prove that we have that our entropy for an irreversible process is equal to dq over t plus another value. Okay, and this other value is what we're going to call the entropy generation. And this is our next part. So it's equal to the entropy generation. So let's define what entropy generation is and come up with a value and a term for it. So in an irreversible process, essentially, we always have entropy being created. So we can say that entropy is created or generated in an irreversible process and cycle. And we also know that it's always positive. We know the entropy created is always positive because if we have no entropy created, that means that we just have we have a reversible process. Okay, if we have a reversible process, we have just ds is equal to dq over t. If we have an irreversible process, we are now creating new entropy. Okay, we're adding a value that is creating new entropy because ds is greater than dq over t. So we can write that we know that ds, and this should be a capital S, so ds is greater than dq over t, and this means that ds is equal to dq over t plus a term called ds gen. So we're going to call S gen our entropy generated. And S gen, we can say that S gen depends on the process. And so we can write that if we rearrange this equation with dq by itself, we can say that dq irreversible is equal to TdS minus TD as gen. So we now have a term called TdS and a term called TdS gen. And if we remember, if we apply the first law to a system and we apply this first law and we say that TdS is equal to du plus pdv, from the fact that we have dq minus d work is equal to du. Okay, just rearranging it, and d work would be turned into pdv. We can say that our d work irreversible would actually be equal to pdv minus td as gen. So we have a new way of approaching the problem that's saying that the work irreversible is actually less than pdv. So what we're trying to say is that our d work in this equation here is actually less than pdv in an irreversible process. Okay, and that's really important. So when we have an irreversible process, our first law is essentially written as follows. It's written as dq irreversible is equal to du plus d work irreversible. And if we have this irreversible process, we now have to plug in our equation for d work irreversible is equal to pdv minus whatever is used to generate some entropy by the losses. So essentially the losses are how the entropy is being generated. Okay, so we can say that work is reduced by an amount proportional to our entropy generation. So TDS gen, the term TDS gen altogether, is also sometimes called lost work. And this lost work is, it's not a real energy, but it's a lost opportunity to extract work. Okay, so it's a lost opportunity to extract more work from the system. Okay, and that means that if we look at a control mass system, so remember that we're looking for now at a control mass system, which is a closed system, we can say that S2 minus S1 is equal to the integral from 1 to 2 of ds, which is equal to the integral from 1 to 2 of dq over t plus S from 1 to 2 generated. Okay, this is our entropy balance essentially. And if we look at our entropy balance, we can say, so from this equation, we can essentially write the change in entropy within our system. If we write it in words, the change in entropy is equal to the plus in, the minus out. So if we have Q in, we're going to have plus in. If we have Q out, we're going to have minus out. And we're going to have plus some generated energy. And this generation would go to 0 if we have a reversible process. But if we don't have a reversible process, then we have this gen. Okay? So this is interesting. And remember, this is for a control mass closed system. Okay? So we're going to start with just a control mass closed system. We'll look at control volume open system after. Okay? Just so we have a different view of it. Okay. So now that we have this equation, okay, so we have this equation, and this is called our entropy balance equation. Okay, we have our entropy balance. How do we increase entropy in a system, therefore? Let's try and answer the question, how do we increase entropy in a system? And to increase entropy, let's just look at what we have in terms of our equation. So what does our equation tell us? Well, we can increase entropy in a system in two different ways. We either have an increase in entropy by transferring heat to the system. Okay, we see that we can increase our entropy if we make this term bigger. If we make the plus in bigger, we're going to have a bigger change in entropy. Okay, we're going to change the entropy in the system by bringing more heat into the system. Okay, the other way to increase entropy is by having an irreversible system. So if we have a very irreversible system, or a system that's very far from reversible, then we're also going to increase our entropy. So we can see just from the equation, we can tell how we can increase the entropy. Okay, so those are the two ways we can increase entropy. How do we get a negative change in entropy? A negative change in entropy within a system, so this is within a system. Within a system, we can have a negative change by doing the following. We can transfer heat from the system. And if we remember earlier when we were doing the aluminum problem with the iron problem, we saw that the change in entropy for the aluminum was negative. It's because heat was leaving the system. Now, entropy overall, if you take the whole system of Earth as a whole, or any system that is big enough, okay, if you take a big system, then the entropy overall always increases. And the reason why the entropy always increases is if we assume that a system is adiabatic. Okay, so obviously if we look at a system that's a heat exchanger and we look at one side of a heat exchanger, the entropy can be negative from one side to the other because heat is coming out of that system. But if you look at the system as a whole and the system is adiabatic, okay, with the outside, with the surroundings. So if you take, for example, a heat exchanger and you say that the heat transfer is negligible to the outside of that heat exchanger, then you can say that entropy overall always increases. Okay, so we're going to stop here for part 3, and we'll see you in part 4 where we're going to discuss the second law for control volume, and we'll do a lengthy example problem where we can understand how to apply the first law and the second law to a problem using our control volume approach. So we'll see you there.